So, welcome to the lecture on design via root locus and compensation techniques. So, in the previous lectures we have discussed how to sketch a root locus, and we saw that root locus is the movement of closed loop poles when the gain is varied. So, it is graphical techniques. Root locus is a graphical technique that displays both the transient response and stability information. So, on a root locus we can find some specific points and we can calculate the transient response information about that point. And we can see whether this transient response information is as per the design requirement or not. Then we can select some other point that better matches the design requirement. However, in this root locus we are forced to select a point only on the root locus, because that root locus is a locus of closed loop poles when gain we vary the gain. However, what happens if we want to design the system for a point that is not on the root locus? So, we can say that if we have this is our S plane and we have some point, this is the, let us say, open loop poles, and so root locus starts so this is our root locus. And we want some point on the root locus, let us say this is some damping line, so this is a constant damping line and this is intersecting at some point, let us say A. Now, we are interested to keep the same damping, or we can say here the same settling time is 4 upon sigma d or 4 upon zeta omega n, and percentage overshoot is function of damping. So, we want the same percentage overshoot or same damping, but we are interested our system to design so that it gives the transient response corresponding to point B. Now, our root locus follow this path, this red line path. So, we can only get by changing the gain, we can only get a response for those points that fall on the root locus. But if a point is not on the root locus, we can't get the response of the system. So, for this point B, our objective is that if we want to speed up the response, so means the settling time is less, because if we go to B, we have the same percentage overshoot because we have the constant overshoot line or damping line, but we have more sigma d because here the sigma d is more. So, if this is sigma d 1 and this is sigma d 2, so minus sigma d minus. So, sigma d 2 is greater than sigma d 1. So, therefore, T s 2 will be less than T s 2. So, we can say T, so here B and this is A. So, sigma d B is greater than sigma d A, and therefore, T s B is less than T s A. So, we get a smaller settling time, means our response is faster. So, we want to design our system for this point, not a point on the root locus, and this we can see here the response. We can see that for this system the response for poles at A. So, here this is the response, and here you can see that peak time is also larger and settling time is also larger. But when we take the response corresponding to point B, we have less peak time and less settling time. So, we have faster response, and this is our requirement. So, therefore, when this is the condition, we can't get this response only by changing the gain. Therefore, we need to change the system, because if we want this root locus to pass through this point B, so that we can get the response corresponding to point B, we need to change the system, because only a changed system can have a root locus that may pass through this point B. But changing a system is quite expensive and counterproductive process, because most of the systems are chosen for characteristic other than the transient response. For example, a motor is chosen for speed and power requirement. So, if we change the system for transient response, its power and speed characteristics might change. So, therefore, we don't need to change the system completely, but we need to augment the system or compensate the system with additional poles and zeros. We can add some additional poles and zeros to the system, and we can augment the system, and we can add these poles and zeros to the before the input to the plant. So, that is the low power requirement. They will need low power requirement. They are low power end of the system. So, we will not affect the output power of the system. So, this process is called the compensation or augmentation, and we will use the root locus method to discuss the compensation techniques, how we can compensate a system, how we can augment a system, existing system, so that it will give the required transient response and required steady state response. Now, when we discuss about compensation techniques, we have two type of compensation. One is that we add the compensator poles and zeros in series of in the forward loop, that is in the series of the plant and before the plant. So, we can see here this, we are going to add here this compensator. This is our original, this is plant, and if there is some original controller, it could be a gain K. Now, here we are adding the cascade compensator, that is in series to this plant. that is G1s. So this is called cascade compensation, and here we can add the compensator in feedback loop. So this is suppose there is earlier there is no any unity feedback, we are going to add some feedback compensator here. So this is called feedback compensation. Now there are some basic elements of ideal compensators. So here when we say ideal compensators, so ideal compensators are able to give us the accurate design requirements, and they are active systems. For example, we add amplifiers, some integrator, or some differentiated circuit. So these need some external power. So they are active circuits, and therefore we call it ideal compensators because they give us very accurate results. There are other passive compensators, or we call it lag or lead compensators. So they don't need external powers. So in this lecture we are going to talk about ideal compensators. So here ideal compensators, we can see here there is proportional controller. So proportional controller gives a feedback by scaling the error of the plant. So if we have here, this is the our input, this is our ES, so here if we add some proportional compensator, let us say K, so K times ES will enter it to the input of the plant. So this is plant, and here gain is a proportional controller. So we are just giving a scaled input of the error to the plant. So this is here we have G1 S equal to K. So the transfer function of this compensator is K. We can also give the integral controller. So we feed the integrated error to the plant. So we give some here, in spite of K, we can have integrator. And so if we have integrator and we represent the transfer function, we can write K by S, because transfer function of integrator is by S, divided by S. So here we can say G1 S for integrator or integral controller is K by S. We can also give a derivative controller. So we give a differentiation to the error and give to the input, and then this will be K into S, because if it is first derivative, its transfer function is, we have Ks. So here G1 S equal to Ks. Now we could have also proportional plus integrator or proportional plus derivative controller. So we feed the scaled plus integrated error to the plant, and so we have K1 plus K2 by S. This could be the transfer function of proportional plus integral controller. So here we can see what I discussed. We have those compensators transfer function, and we can add these systems before the plant, so we can compensate our system. So let's discuss the ideal integral compensation, and we also call it PIR, proportional plus integral compensation. And the objective of this compensation is to improve the steady state error without affecting the transient response of the system. So here we have to improve the steady state error, and because we are talking about the ideal compensator, so we should be able to achieve the zero steady state error also without affecting the transient response. Because if we improve the steady state error and we affect the transient response, then we are one design requirement we are fulfilling, but other design requirements we are affecting. So here we have to improve the steady state error without affecting the transient response of the system. So to achieve this, we can have a compensator that is called PI compensation, proportional plus integral. So we can have a pole at origin and a 0 close to the pole. So we place an open loop pole at the origin, and because this increases the system type. Because we know that if we want to improve the steady state error, then if we could increase the system type, then we can reduce the steady state error. Because we remember that when we had a type 0 system, for that we said that n should be greater or equal to 1 for a 0 steady state error. Means if we put at least one pole at the origin, then for a type 0 system the steady state error will be 0. And if it is type 1 system, so for the ramp input we can have n greater or equal to 2. So there should be 2 poles at the origin. So now here if we take a type 0 system and we want the improve the steady state error, we can keep one pole at origin, so it will improve the steady state error to 0. But it may affect also the transient response, and that we have to stop, because here the objective is only to improve the steady state error without affecting the transient response of the system. Therefore, suppose if we have this system, so we have input, we have this ES, here K and GS. So let's say this is gain and this is our plant. So this is our plant, and if we plot this root locus for this, let's this GS has 3 open loop poles here, and we have a root locus and we have a point here A. So here this angle theta 1, theta 2, theta 3, and we have these are all three poles. So, minus theta 1 minus theta 2 minus theta 3 should be equal to 2k plus 1 180 degree. They are okay because this system for this the root locus we are getting this condition. Now, when we are going to add one pole at origin, so what will happen? We have this is a compensator. So, now this is a compensator. So, this compensator, with this compensator we will have, we will change the root locus, and it is possible that this root locus does not pass through this point A. So, we have now this one pole at origin and these three earlier GS pole. So, now the root locus will lie here in this and here. So, this root locus may move like this and like this. And here is our point A. And it does not pass through point A. And here we have so this is theta C. So, theta C is the angle of this compensator pole, and these angles are already this theta 1, theta 2, theta 3. So, here minus theta 1 minus theta 2 minus theta 3 minus theta C, that will not be equal to 2k plus 1 180, because at this point A it was 180, this condition was satisfied, but now the root locus is changed and this condition will not be satisfied. So, what can we do now? This additional angle that is made due to addition of this pole, if we add a 0 close to this pole, so this angle will also be made almost equal and opposite sign. So, this will be cancelled. So, here if we add a pole, a 0, so if we change this as k s plus a, so we are going to add a 0 that is at minus a. So, here what will be the root locus for this? So, again here we can have this is the pole at 0, compensator pole, and here we are putting a 0 near by, this is compensator 0, that is minus a. So, this minus a is coming here, and these three poles, and here is this point A. Now, this pole root locus will start this pole and end at this pole. Now, this will start here, end at here, and this will go here. So, again this root locus will change and it may start going through this point A. So, we will have this angle. So, let us say this is PC, pole compensator pole angle. Now, here we will have so this is theta PC and the other angle is theta 0, compensator 0. This is theta 1, theta 2, and this is theta 3. So, again here minus theta 1 minus theta 2 minus theta 3 minus theta PC plus theta ZC equal to 2k plus 1 180 degree. So, of course, here this will approximately equal to, because this theta PC is approximately equal to theta ZC and they are opposite signs. So, they will almost cancel, and so this condition will remain that was here initial condition, and therefore, we have improved the steady state error by putting this pole at one pole at origin, because system type is increased, and so steady state error is improved. However, at the same time we have, by adding a 0 close to this pole, we have retained the transient response requirement of the system. And so here we can see what we discussed here, the same thing we can see here, and these are these two other compensated root locus, and this is the final one. So, we are getting this root locus as original. Now, how to represent this root locus? How to represent this ideal integral compensation? So, we can see that here we have Ks plus A by S. So, we can represent it as individual circuits of gain and integration. So, individual circuits are so here we have so we can have here, let us say K1 So, here we have this, we are talking PI controller. So, here this is proportional plus integral. So, here this part is proportional, because here this is ES coming, and so proportional to this error. So, scale 1 going here, then this is the integral, because here is a integrator, and this integrator we represent as a transfer function K2 by S, and so therefore proportional plus integral, that is going to be summed. So, here G we can have, this is, if this is GCS. So, GCS equivalent of this proportional plus integral. So, that is K1 plus, because here K2 by S. So, this is equal to k1 1 plus so s plus k2 by k1. So, here we can see that here we have a is k2 by a equal to k2 by k1 and k1 equal to k. So, the location of a, that is the 0, can be adjusted by varying these k2 and k1. So, here we discussed the ideal integral compensation, that is proportional, also called proportional plus integral compensation, and we will continue this compensation and others in the next lecture. So, I thank you for attending the lecture and see you in the next lecture.